Yeah. All right. Okay, we're going to talk about complexity theory.
Non-deterministic Philip.
Non-deterministic Philip and Philip space.
When you draw those arcs like that, I mean, should we be filling those in as complete circles, or is that because there's going to be some funky overlap?
Well, Neil's not here, so I stopped making bullseyes because he said he wants. No, they're complete circles. So. And I'm actually going to fill more in, so I'm not making a big picture yet. I just want to fill in enough so that it makes sense today, and then we'll fill it in a little more. So when you talk about complexity theory, you're talking about problems that you can already solve that are for sure in the decidable area, and you're wondering about how much time and space they take to solve. So problems that are in here are in polynomial time, like checking if a list is sorted, like finding the shortest path between two nodes. Problems out here are problems that you can do in polynomial time, but you're allowed non-determinism. So if you remember what that's like from the algorithms class, you can guess stuff and then verify it in polynomial time. From this point of view, from this class point of view, it means that you can have a non-deterministic Turing machine that does it. So that means, imagine if you have to try something and then check that it works. Non-deterministically, you can have an arrow that tries all of them at the same time. So the question is, how do you determine how much time it takes for a non-deterministic Turing machine to run? We're going to talk about that because it's very intuitive. But before we do, I just want to remind you, how much time does it take for a regular Turing machine to run that's deterministic? It's the number of steps it takes for it to say yes or no. Okay, that's the amount of time it takes. And let's say a particular Turing machine, has an infinite number of inputs, and for every single input, say of size n, the number of steps it takes is bounded by some constant times n squared. Then you'd say that the algorithm runs in order n squared, just like you do for programs. So you measure it the same way. But you can't say that a Turing machine runs in n squared on a particular input. That doesn't make any sense. Like if this input is 7 and the number of steps it takes is 49, it's true that that's n squared, but that doesn't mean that the whole algorithm runs in n squared, because maybe you have another one of size 10 and that takes 2 trillion steps. So to say that an algorithm runs in n squared or that a Turing machine runs in n squared, it's got to be something that works for every single string in the input, not just the particular one. Okay, so that's regular normal time. Space is not how many steps the Turing machine takes, but how many distinct cells on the tape it visits. So in general, if you use, say, n squared space, you have to have used at least n squared time, because you have to visit those places to write things there. So anytime you visit a cell, it takes at least one step. You can visit them a lot and go back and forth plenty of times and have your time be much more. But in general, polynomial space algorithms are going to contain polynomial time algorithms, because anything that takes polynomial time also takes polynomial space. Okay, because just doing that many steps.
Other way around.
Other way around?
The polynomial space problem is also polynomial time.
No. If you have an algorithm that runs in polynomial time,
okay,
then it takes polynomial space, because it can't. Because if it takes 10 steps, then it's seen 10 symbols. If it takes n squared steps, it seems at most n squared symbols. But it's possible to see n squared symbols on the tape and take much more than n squared time. Right? You can see n squared symbols in the tape and go back and forth an exponential number of times, just visiting those symbols and writing different things in them. So polynomial space contains polynomial time. Things you can do in polynomial space there's more things you can do in polynomial space. So to say that an algorithm runs in n squared or that a Turing machine runs in n squared, it's got to be something that works for every single string in the input, not just the particular one. Okay, so that's regular normal time. Space is not how many steps the Turing machine takes, but how many distinct cells on the tape it visits. So in general, if you use, say, n squared space, you have to have used at least n squared time, because you have to visit those places to write things there. So anytime you visit a cell, it takes at least one step. You can visit them a lot and go back and forth plenty of times and have your time be much more. But in general, polynomial space algorithms are going to contain polynomial time algorithms, because anything that takes polynomial time also takes polynomial space. Okay, because just doing that many steps.
Other way around.
Other way around?
The polynomial space problem is also polynomial time.
No, no. If you have an algorithm that runs in polynomial time,
Okay.
then it takes polynomial space because it can't. Because if it takes 10 steps, then it's seen 10 symbols. If it takes n squared steps, it seems at most n squared symbols. But it's possible to see n squared symbols on the tape and take much more than n squared time. Right? You can see n squared symbols in the tape and go back and forth an exponential number of times just visiting those symbols and writing different things in them. So polynomial space contains polynomial time. Things you can do in polynomial space are, there's more things you can do in polynomial space intuitively than you can do in polynomial time. And we're going to talk about particular examples of these later. All right, so before we talk about any more about the relationship between these classes, let's talk more about this class in between. I haven't proved to you that it's in between. You know that it's bigger than P. I haven't shown you that it's really less than P space yet. We'll talk about that later. But for now, what does it mean to have the time of a non-deterministic algorithm? Here's the way to think of Turing machines from now on. Stop thinking of them in terms of these detailed, low-level, transition things. Think of them in terms of more abstract things that are easier to analyze. In particular, you're going to think of them in terms of graphs. An algorithm that's deterministic looks like this. It starts in the initial configuration of the machine, and then it goes to another configuration, and it goes to another, and it goes to a few more, and sooner or later it stops and says yes, or it stops and says no. The computation of a deterministic machine looks like a straight line. Okay, and each of these dots is a snapshot of the machine. What does a computation of a non-deterministic machine look like? This is different. A non-deterministic machine starts here, and it might have more than one choice. So in order to represent this computation, we have to consider all the possible choices. And here's what it might look like. Let's say there's 4 choices. And let's say here there's 2 more choices, and out of this configuration there's only 1 choice, and out of this one there's 3 choices, and out of this one there's only 1 choice. And we keep going this way to new and newer configurations until sooner or later one of these branches ends up at a state that says yes. Then we accept. A non-deterministic machine accepts its input if one set of these choices, if you can find your way from the initial configuration, work your way down through the tree and find one leaf at the bottom that says yes. What if there's 1,000,000 leaves that say yes? That's okay, as long as there's one. What if there's 1,000,000 that say no? That doesn't matter. As long as there's one, this machine accepts its input. So the accepting computation is still a line. It's a single line. But the whole computation possibilities is represented by a tree. Everyone understand the difference? Okay.
Is there a concept of once you're at a path of length b, there's no sense of going to b plus 1?
Well, that's a good question. So that has to do with the question I was going to ask you next. How much time does it take to accept a string in a non-deterministic polynomial algorithm? How do you measure the time? Well, here it's obvious how you measure the time. You count the steps. How do you measure the time here? Well, what do? It's a definition, so there's no, there's a right answer, but it's arbitrary. We just decide how to measure the time here. The idea of a non-deterministic algorithm is that it gets all these choices ORed together, and it gets them for free. You can try them all, in some sense, at the same time. So it's getting power for you. And the amount of time we actually measure is not the time it takes to look through this whole tree and find a yes on the bottom, but simply the time it takes to find one branch to the bottom. So this represents all your guessing for free. You guess this choice, you guess this choice, you guess this choice, and you just have to verify that it works. So the time it takes to run a non-deterministic algorithm is just the time it takes to get from the initial configuration to the place where you accept. Just the depth of this tree. Yeah.
Why is the 2-player game thing different then? Because isn't that just a tree also?
It is a tree also, but the nodes don't connect with ORs. Each level connects with an OR, and then the next level connects with ANDs.
But isn't it the same thing that I want to get to an accept state at the bottom?
Yes. Let me get to it later. It's a good question, and it needs to be clarified, and I haven't clarified it yet, but I will get to it. So in this case, it's just one little branch that represents the computation. What if there were lots of different places to find yeses? Then which one do we count as the time it takes to do that string? What if there was one that went down here, Yes. And one that went down here? Yes. Which one do you count as the time it takes? The shortest one. Okay, so that's the official definition. If the non-deterministic algorithm accepts a string, the time it takes is the distance from the initial configuration to an accepting configuration. That's the shortest one. Okay? Everybody understand that? It's technical, but we have to make sure everybody's on the same page here with the definitions. Okay, questions about this? I'll get to your question, but not just yet. It'll take a little while. Okay, so here's the first thing I want to do. I want to convince you before we go into anything more that this picture is really true. That P space contains P, and that P space contains NP, and that NP contains P. That it goes in this order. So two of these are very, very straightforward. NP certainly contains P, because non-deterministic polynomial algorithms can do everything polynomial algorithms can do. You just don't have choices on them. I mean, everything in here is by definition something in here. So that's just the special case of this. That relationship is by definition. P space contains P because of our definition of space and time. Space means how many different cells you visit on the tape. Time means how many different steps you take. So if you have something that takes 30 steps, it's got to take at least, if something that takes, did I say that right? Something that takes 30 steps is going to take no more than 30 cells. Right? Can't visit anymore. So anything that's time f of n is going to be space f of n. It's going to be inside it. Right? So what about NP? How do you know that NP sits in between? Maybe NP is way out here. It turns out that anything that you can do in non-deterministic polynomial time, you can do in deterministic polynomial space. And the reason for this is based on something we've already done, and I'm going to review what we've done and analyze it as we go. So here's what we're going to do. Somebody gives you a non-deterministic Turing machine that runs in polynomial time. They're telling you that's the case. And you take it. It's called M. It's non-deterministic. It's polynomial time. An example for M is something that solves the Hamiltonian circuit problem. It non-deterministically chooses a sequence of vertices and then checks that they actually all connect together and make a circuit. We've done a lot of these non-deterministic algorithms in the algorithms class. So there's a non-deterministic polynomial time algorithm. How are you going to simulate this without non-determinism? If you take the non-determinism away and you have to do the same algorithm without the non-determinism but just determinism, what do? We talked about this when we went ahead just to prove that anything non-deterministic done in a Turing machine could really be done deterministically. So let's do it, but this time let's keep our eye on how much time and space we pay in order to do this simulation. Okay? So we're going to do the same simulation, non-determinism to determinism, but let's watch what happens to the time and space. Let's see if it grows. All right, what do? How did we simulate non-determinism? We can make this picture again. Here's a non-deterministic machine. It's essentially a big, big graph like this. The machine describes to us the choices at every step. And we can build this graph, or this tree, as deep as we like, and it represents the possible computations of this machine. And what we want to do in order to decide whether a string is accepted by this machine or not, this machine's magic. It just makes the right choice and finds it. If we want to do this deterministically, we actually have to look through this tree and find a path that goes from here all the way down to a leaf that has an accepting configuration. So how do we do that deterministically? We just do a brute force kind of algorithm. Let's say that the maximum number of choices at any node is 4. Say it never gets bigger than 4. There's going to be some maximum number of arrows that come out of a node. If the maximum's 4, then here was our plan. We have one tape that we keep the input on, and we leave that separate. We have one tape at the bottom here that's used for simulating the program of this non-deterministic machine. And then we have one tape that tells us which choices to make while we simulate. So the first thing we do is we simulate this machine with one step. And that one step can either be, and I'll expand this over here, it can be a 1, a 2, a 3, or a 4, corresponding to these 4 choices. So we write our deterministic Turing machine to generate these numbers in order on this tape. And then we take the finite state machine of the non-determinism, and we go ahead, look at this input, and simulate it, making those choices one at a time. And we check after each one whether we have succeeded and hit an accepting configuration. Now, after one step, we're not likely to find an accepting configuration, so we go on and do it now for 2 steps. But now for 2 steps, what's it going to look like? You can do 1, 1, 1, 2, 1, 3. Let's do just this example. 1, 1, 1, 2, 1, 3. You can also do 2, 1, 2, 2, 2, 3. Then you can do 3, 1, and 3, 2. And then you can do 4, 1, and 4, 2. And these numbers that you generate on this tape represent taking the computation first this way, then this way, then this way. We are just doing a breadth-first generation of this tree, step by step by step, looking to see if we ever get an accepting configuration. We are just generating every possible leaf of this tree, one by one in a systematic way, deterministically. And you could write a Turing machine to generate these numbers deterministically and simulate each time.
Isn't that on the tape growing exponentially, though?
Well, let's talk about that right now. Let's talk about, well, before we talk about that, let me make sure everybody gets the simulation. Are there questions about what we're doing here? We're turning non-determinism to determinism, and now what we're going to do after we realize that it's really doing what the non-deterministic machine is supposed to do, and doing it step by step, let's measure how much time and space it takes, which is what Chris is asking about. So what do we pay to do this? This machine is guaranteed to run in non-deterministic polynomial time. That means the number of steps it takes on this simulation is polynomial in the size of the input. So let's see how much time we pay. Every one of these simulations is going to be polynomial because we're just simulating the old machine. So that's not going to be bad. We don't do anything with this tape. That doesn't give us any time. What about this tape? This tape is where we're really slowing ourselves down. We do a lot of these simulations. How many do we do? Not just one. First we do 4 of them. Then we do potentially, what's the most here? 4 times 4. We could have gotten 16 possibilities. Then we do 4 times 4 times 4. Yeah?
The yes or no
Yeah?
for this non-deterministic machine has to come at the end, right?
Yes.
So I don't understand why we have to simulate 1, 2, 3, 4 if those aren't.
Oh, we don't know when the end's going to come. For all we know, it stops after one stage and says, I accept. Like, let's say this non-deterministic machine runs in n squared time. That means it never takes more than n squared steps on any input. But on some inputs, it might take 1 step. It doesn't have to take at least n squared steps. In other words, it's possible that we stop after 1 step and say, yes, I accept that string. So we have to check that. We just don't want to generate way down at the bottom to go past an accepting configuration and then miss it. Do you get it, Seth? All right, well, how far might we go here? Here's 1 step, here's 2 steps. You got to go 3 steps. How many steps do you have to go? Well, I didn't tell you what this polynomial time thing was. Let's call it f of n. This is going to find an accepting computation after f of n steps at the very worst. Could be n squared, could be n cubed. So this is 1, this is 2, dot, 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 dot. This is the list for the f of n steps. How many different things are in this list? Here we had 4 to the 1. Here we had 4 squared, possibly. Here we're going to have 4 to the f of n. This is how many different sequences of numbers will appear successively on this tape when we finally get to the bottom, at which point we know we can stop simulating. Right? I mean, if you don't get it after this point, you can just stop. You don't have to keep going further. You can say, no, it's never going to accept. It's going to be in some infinite loop, because you've got a bound on how long it's supposed to take. That's kind of an important stopping point. That means you never have to simulate this forever. But you do have to go this far, and this is a lot. 4 to the f of n sequences of strings here. And every one of them has to be written on this tape. That's a lot of time. you're paying a big amount of time to go from non-determinism to determinism. And here's where you're paying it. You're paying it in this exponential amount of strings that get written on this tape. Each one of them gets simulated by the original machine, which takes how long? Which takes f of n. 4 depends on the maximum number of arrows out of a state. So it's constant, but it could be 4 or 6 or 8. In any case, it's exponential and it's bad. So what we've shown is, well, here's what we have shown, and I'm going to write it down. It's definitely exponential. It's not worse than exponential, right? It's exponential times some linear. So I'm going to make a new class out here called exponential time. And I'm going to write that exponential time contains non-deterministic polynomial time. Because anything you can do in non-deterministic polynomial time, I just showed you can do in exponential time. Right? So that's something else we just figured out now. We still don't know why this is in here, but we'll get to that in a second. Let me stop for questions. All right, so this is at the heart of the P equals NP question. The fact that when you go from non-determinism to determinism, you pay for it with exponential time. And nobody knows how to do better. It would be great if we knew how to do better. But nobody knows. Questions about this? Yeah, Teresa?
What is a time step when you do the first level and you just have 1? Is that one time step? And then when you're in the second level, do 1, 1. Is that still one time step?
No, these are 2 steps.
Those are 2 steps.
Right. This contains all the possible 2-step computations on the original machine. And we can go this way and this way, or this way and that way. So this represents visiting each one of these places on the computation.
And we redo step 1, even though we already did it once. We still have to redo it in level 2 each 3 times for each of the 3 first possibilities. You know, 1, 1, 1, 2, 1, 3. We don't just like copy it.
You could store it somewhere and then continue from where you left off. But it wouldn't help the time too much.
Because you got to go find it? Or
because even if I just counted...
We counted that as 1 step rather than 2 the next time.
Even if I did that, even if I just counted this as, in fact, I'm really doing that. I'm counting doing this as 1 step.
Okay.
It's still 4 to the f of n at the end. So if I really counted doing it all the way from the beginning, it would just multiply it all by 4. When you count just the leaves at the bottom, they equal exactly the sum of all the other nodes put together. So including all of them, as opposed to just including the leaves, just doubles this number, but it won't change how bad it is or make it better. Yeah, it's a good question. I mean, there's a technicality there. And I'm really not actually including how much time it takes to get to the bottom. I'm not saying that it takes 2 steps. I just figured it takes 1 step to do this. But really, actually, it's not 4 to the f of n. According to what you're saying, it's really 4 to the f of n times, like, log f of n, the size of this number. I mean, it's true. But, I mean, the point is it's bad enough here. We don't have to worry about those details. All right, how much space does this take? It takes a lot of time, but how much space does it take? I want to convince you that it only takes a polynomial amount of space. And that's why polynomial space contains this. It doesn't take exponential space. Why not? Chris thinks it does,
Well,
right?
It looks like you do, because you're printing out all of these exponential multiplications of...
Well, if we really do it like this and print them all out on the tape and then do them one by one, it will take an exponential amount of space, and that's bad. But there's no reason we have to write them all out. Why don't we just have our machine generate them one by one? So it generates 1, 1, and it goes down, and it checks it. And then when it's done, it erases this, and now it generates 1, 2. It never actually keeps them all on the tape at the same time. It just keeps one of them on the tape, erases it, and does the next one. You agree you can do that? OK. So if you do that, then what's on the tape? What's the worst thing that's ever on this tape? How long does this tape ever get? What's the longest thing? Right, it's the longest one. It's just one of these. So the amount of space that ever gets put on the tape is f of n sequences. Actually, each one is kind of long. I mean, by that time, each one is almost f of n, or log f of n long. But it's no worse than f of n times log f of n, or f of n squared. It's certainly polynomial. The trick is not to put all these on the tape when you do it. And that's equivalent, if you think this is too abstract, think about this. That's equivalent to if you're writing, remember that Java program you wrote that did that game with the balls? And you try to figure out a way to play that game so you get the best score? Well, one way to do it is to actually store the whole tree and then look through it. And you're computer crashes because there's not enough memory. You get a stack overflow. The other way to do it is to build the tree a branch at a time, storing only the path up to where you're up to, and then backing up and then going forward again, erasing the part that you've gone on. So, I mean, this is completely practical, and people do this all the time. You wouldn't keep all this in the memory. You just do it one at a time and create the one you want next. All right, so that shows that p space contains NP. It also shows that exponential time contains NP. We already know that NP contains P and P space contains P. So now we're almost finished this whole thing. How do you know that exponential time contains P space? Let's talk about that, and then we'll take a break and review our figure. So here's the last enclosure, exponential time containing P space. So that means somebody gives you a deterministic algorithm. It runs in polynomial space, and you want to simulate it. Here's the tape. A polynomial amount of space is used on this tape. And you want to simulate this Turing machine and figure out what's the worst amount of time it's going to take to simulate this Turing machine. So your gut instinct, before you think too hard about it, should be, well, how do I know? I can just keep running and running. Is there any upper limit at all? And this is a really important point. There is an upper limit, and it's based on a very, very, very crucial idea that comes up again and again when you analyze programs. Here's how I'm going to simulate this polynomial space deterministic machine. I'm just going to run it. And I'm just going to keep track of how much time it takes. Right? So it's running and running, tick, 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 lots of times going by. But I know that I'm never going to use more than this polynomial amount of space. I run it and run it and run it, and it's not ending. And it runs and runs and runs and runs, and it goes on and on and on, and it runs, and 280 years have gone by, and I left a little note in my will for my kids to keep running it, and it keeps running. So what have I shown? I've shown that polynomial space is contained in infinite time algorithms. Well, that's true. So can we knock it down a little bit better? Can I knock it down for exponential time? Can I leave a little note to my great-great-grandchildren to say, if it ever takes more than this amount of time, stop! You're never going to accept it. That's what I'd like to do. Everyone understand what I'm hoping for? If I can't do that, then I'm really stuck. There's no way for me to have any time bound at all. But what I want to convince you is that if there's a polynomial space bound on your Turing machine, then there's no issue of undecidability or infinite loops. You can always stop at a certain point and know for sure whether the machine is going to accept or not. And here's why. Let's say this machine has 3 states. And let's say it has 2 symbols, 0 and 1, and the blank, of course. So 2 symbols, 0 and 1. And, of course, the blank. So polynomial space means that only a polynomial amount of spaces have 0s and 1s in them ever. Nothing else has been touched. And the head, of course, can be on any of these symbols. So what we're going to talk about for a moment is how many different configurations this machine can have. If you turn this machine off, you need to remember what it looked like so you can start it up again. There's only going to be a limited number of configurations the machine can be in. And because of that, if you let it run long enough, it's got to hit all of them. And if it ever goes from one and hits that same one again, then you know it's in a loop. Just like the finite state machine hit a loop on the same string of symbols. Now this doesn't happen often with Turing machines. If you don't have any space bound, you have no idea if the machine's in a loop because it can keep using new tape cells and the configuration keeps changing and changing. But if you restrict the machine to just using this much space, you've essentially bounded that machine's computation, and it doesn't have an infinite variety anymore. It has a bounded variety. Just not a finite number of computations, but finite relative to the input. So for example, let's say this polynomial space algorithm is n squared. Let's just give it a number. And let's say I put in an input of size 10. That means that I have how many cells here that could possibly be used? 100 cells. Right? 100 useful cells on the machine. I know the machine will never, ever go past 100 cells. I'm guaranteed. I'm given that. Let's figure out how many different configurations this machine has exactly. How many different snapshots of this machine are identifiable? Well, how do you identify a configuration of a machine? You need to know what state it's in. You need to know where the head is looking at. And you need to know what the tape looks like. Now, the tape is essentially finite here. There's only 100 cells. How many different sets of zeros and ones can I put in these 100 cells? Two. It's like how many binary numbers are there that have 100 digits? 2 to the 100th. This represents the different tape configurations. That's not all. For each of those, I could be in any one of these three states. Times 3. And for each of those three states and for each of these configurations, my head could be in how many different places? 100, right? It could be in front of the first one, in front of the second one, in front of the third one, all the way up to in front of the 100th. I'm going to rewrite this in general. Q is the number of states. K is the number of symbols on the tape. S of n is how much space I have. And this is the number of configurations in a machine with Q states, K symbols, and S of n space. Here's the specific example. Here's the general way of looking at it. Here's the point. When you start running this machine as a deterministic algorithm, you just run it, but on a separate tape, you go ahead and look at the number of states, look at the number of symbols, look at the alleged space function, calculate that on the size of the input. So you calculate this 100 and this 3 and this 2, and then you calculate this number, and then as you simulate the machine, you start counting. 1 step, 2 step, 3 step, 4 step. If during the simulation you ever accept or reject, then you accept or reject. You're all done. And that's a fine simulation. But what happens, the only problem is, what if the machine keeps running and running and running and running, and sooner or later it takes more than this many steps? At that point, you know that two configurations that are identical have occurred during this computation. If that happens, it means you did something like this. Configuration, 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 dot, dot, dot. 2 million later, configuration, there. Once this happens, you are stuck in a loop that will go forever. If you didn't accept up till here, you're not going to accept if you continue. Because whatever happened from here down is going to happen again when you get back there. The machine looks exactly the way it did when you were here. If you turned it off here and you went down this loop and turned it off again, and you asked the person what's the difference, they would not be able to tell any difference in the machine. It looks the same. So it's in an infinite loop. The point is, if you have a space bound on your Turing machine, you can tell if it's in an infinite loop by counting enough steps. When it's past the number of configurations in the machine, you know there's an infinite loop. Okay. Are there questions about that idea? That's a fundamental idea, that bounding the space lets you bound the time also. And that's why exponential time contains polynomial space. Here's the exponential time. This much time to simulate S of n space.
An input size of
On an input size of n. Right. On input length n. Right. Space Tm. All right. Questions about this? Stuff tricky, huh? So this picture is now justified. It really does have that hierarchy and that structure. Teresa, you have a question? What are you thinking about? Okay. Gary, okay? Yeah. All right. Good.
In this kind of a world, we don't care at all if the time is in any way. I mean, 2 to the 100 is obviously not a reasonable time, but we don't care if it would end before eternity. That's
right.
Good enough.
Well, this is right. Well, it's exponential time, right? There's super exponential time too. It's not that. It's not 2 to the 2 to the something. You're thinking this is weird? There's a problem that you can prove. It's one of the few problems you can prove actually requires exponential time. There's a problem that you can prove actually requires exponential time. It's not exponential time complete, where if it's solvable, then everything else is solvable. It's even stronger than that. It really needs exponential time. And it's not some whacked out weird problem. It's take two regular expressions where you're allowed to do this. Instead of just 0 star and 0 plus 1 or something, you're allowed to put in stuff like this, 1 to the 10th. You're allowed to use exponentiation, just like in your regular expressions you use in any language, where they probably let you do just that. Two regular expressions that let you do that, are they the same, yes or no, has to use exponential time. So don't start writing algorithms to do that. Regular expressions are hard to compare. Do they generate the same language? Very, very hard. That's way out here. So yeah, it's not practical, but that problem is one that a naive student is going to try to do one day. And it's nice to know that better come up with a better way to do it. Other questions about this? All right. This little bullseye thing goes down 2 levels also. And our book talks about these levels, and I'll put them in for completeness. It's one here and one here. This is non-deterministic log space, and this is deterministic log space. The book calls these NL and DL. This means you have a non-deterministic machine that uses logarithm space, and this means you have a deterministic machine that uses logarithm space. We just showed that exponential time contains polynomial space for the same reason, for the exact same reason, no difference in the argument. Polynomial time contains deterministic log space. Just take this logarithm space and raise it to a power of 2, and you get a polynomial. 2 to the log n is linear. So polynomial time does contain deterministic log space. Non-deterministic log space is in between. People like to know how these classes really relate. I wrote it in this way because these are containments. But are any of these really proper? Maybe these are all the same. There's only one level that anybody really knows today is proper. People know that there are things down in here. I'll circle this little circle area. Things in here that cannot be done out here. So there is really a difference between this level and that level. There's a hierarchy. There are things that take polynomial space, and you can't do them in logarithm space. And we can prove that. It's not a hard proof. There's a hierarchy that breaks up this from this. But nobody knows if P and NP are the same. Nobody knows if P space and NP are the same. Nobody knows if P space and P are the same. Nobody knows any of those things. People do know that exponential time and polynomial time are not the same. Okay, so there is another hierarchy. There's a little barrier between here and way out there. Right, so there's a few things we know about proper containments, but a lot of things we don't know. When we don't know, then we invent this idea of a complete problem. And I want to remind you what that is. You've seen it before a number of times, but I just need to remind you. A problem is complete in a particular ring of the bullseye when every other problem in that ring reduces to it. So for example, this little problem here, that x is NP complete. Two conditions. A, all problems in NP reduce to it. And B is kind of a simple condition. Itself is an NP. That makes a problem NP complete. in some sense, it's the hardest problem. If everything reduces to it, everything reduces to this problem, all the things reduce to it, that means that it's harder than all those things, or at least as hard. So showing that everything reduces to your problem means that solving your problem solves all those other problems. And that's at least a way of identifying which of the problems in these rings are hard, are less likely to be further down in the chain. The harder the problem is, the less likely it is to be further down in the chain. If the second condition doesn't hold, if you can't actually know that it's in NP, then we say the problem is NP hard. For example, it's possible for a problem to be way out here in P space, and you have no idea how to put it into NP, but it still turns out that every single thing in NP reduces to it. It's kind of not so surprising. I mean, you have no idea of even getting it in here. The fact that it's probably harder than all the problems in here isn't so surprising if you have no idea even how to put it down in the set. So it's not as interesting to have something be just NP hard, but there is that terminology. It means everything still reduces to it from NP, but itself, as far as anybody knows, still might be further out from NP. There's no way to actually nail it down. So it's not really the hardest representative of the class. It means it's as hard as anything in this class, and we don't even know what's in the class. It's probably further out.
So in order to turn something from NP hard to NP complete, you have to reduce it to something else.
No, to turn something from NP hard to NP complete, all you have to do is show that it can be done in NP.
Right, and to do that, you would reduce it to another.
You could do it that way. Or you could just come up with a direct NP algorithm. Right. Usually you just come up with an NP algorithm. These complete ideas go for every single class. There are complete problems for every single class that we don't know a containment difference from. So we don't know P space is the same as NP or P space is different from P. So we have P space complete problems. Problems that you know how to do in P space, but that everything in P space reduces to that. So if you could solve those problems in polynomial time, everything in P space would be polynomial time. So we have complete problems for any class that we have questions of containment about. Okay, I think we need to stop for a minute just to look at the diagram, digest what we've done. I'm going to do some more specific stuff in a minute, but let's just take a minute and look at this picture. What's missing in this picture? If you were just looking for patterns, even if you didn't understand a thing about what these classes meant, there's a pattern that's kind of missing. There's something that we didn't put in. We didn't go further down and do log time. That's true. That would be even inside here. But there's very few things you can do in log time. And you know why? Because usually you have to look at the whole input to do anything. And log time means you're looking at, you just have very little time. But people still like the idea of log time. So you know what they do? They just kind of invent that, all right, here's your input, and here's your special tape, and we'll just count how many steps you take on this special tape. But anything in log time means you can actually solve the problem without looking at the whole input. So there's hardly anything useful or interesting like that.
Searching.
Things
like searching. Searching in a sort of...
Like log n time, sure. Things like searching, right. I guess that is interesting. I take it back. What about log space? I mean, you have to look at the whole input. Doesn't that take n space? Is there anything less than n space? So to define log space, you always imagine you have two tapes. One that holds the input, that doesn't count, and one that holds your work area, and that's what you actually count for your space. It's reasonable, really, because you want to really check how much extra space you use. And there are lots of things you can do with just log extra space. But there's still something missing here. Michael's right, the log time's missing for a reason. But there's something else that's missing for a reason. Right, how come I didn't put non-deterministic polynomial space in, right? I stuck in non-determinism at every level, and I didn't stick it in after polynomial space. I just left it be deterministic. So it's not there because it's the same. dp space is the same as np space. They're exactly identical. That's not obvious. But it's a really nice result. Because if the most famous problem in computer science is p equals np, because these two separate and nobody knows why or how, or why we pay exponential time to go from determinism to non-determinism, it's kind of interesting that when you pay space to go from determinism to non-determinism, you don't pay anything. You get it for free, at least as far as a polynomial measure can distinguish. If you have a polynomial time non-deterministic algorithm, you can simulate it directly deterministically in polynomial space with no extra cost. So what is the cost there? We're going to have to refine this class a lot more to see what the cost is. And we're not going to do it right this minute. I'm going to do something else, but I'm just going to tell you the name of this thing. It's called Savage's theorem, named after the guy who created it. And I'll tell you his theorem, and I'll prove it later on, but not right now. Here's what his theorem says. His theorem says that if you have a non-deterministic machine that takes this much space, non-deterministic, S of n space, then you can do it deterministically, and guess how much space you need? You can do it deterministically, and how much space? Anybody read this or guess? Take a good guess. S squared of n space. You square the space, and you get determinism. So that's great. You don't get this horrible exponential explosion. You just get a polynomial explosion. It's not much of an explosion. It's kind of like a little pop. So if you're talking about polynomial space, squaring something in polynomial space stays polynomial. That's why non-deterministic polynomial space is the same as deterministic polynomial space. Because squaring anything polynomial is still polynomial. So these two classes collapse on themselves, and that's why I didn't put it in. And this theorem is really nice. This theorem is not weird and abstract. This theorem is a recursive algorithm that's a good assignment in a scheme class. It's just a really cool way of simulating this without using too much space. And we'll get to it later. I mean, it's really worth seeing, and we will get to it. And because of this, it implies all sorts of collapsing that happens in this hierarchy. That non-determinism and determinism for space, you usually don't separate it. Hey, so how come I separated it here? Well, I mean, I should be able to, what could I put around n log space? According to his theorem. I could put d log squared space. And I could do it. But I can't put d log space there. These two aren't the same. Although it's true that I could put a circle around n log space that says d log squared space. These are particular functions, not just general polynomials. And that's why here there's a difference and here there's not. Okay? So I could put another circle around and do d log space and then put n log squared space around that and then d log to the fourth, and you'd see this long hierarchy of things. All right, we'll get back to Savage's theorem in a little while. Are there questions before we go on? Questions about the big picture? Anything about this? Right. I want to do two more neat things today. One is Savage's theorem, which I'll do at the very end because I think it's really neat. And one is about p-space complete problems, to show you an actual reduction of a p-space complete problem. But before I do it, I just want to give you a sense of at least what theoreticians do when they see this diagram. They really like this stuff, and they look at it, and they love to figure out more explanations and relationships between these classes. So they come up with all sorts of new definitions. And the more carefully the new definitions fit in with this picture, the happier and more elegant they feel it is. So just to give you an example, and I'll talk about this example on another day in more detail, but just one example. Here's a non-deterministic Turing machine. We talked all about it. You know, it's got these choices. And if either this or this or this leads to an accepting configuration, we say yes. You all know what a non-deterministic machine is. I once mentioned when we talked about finite state machines, why don't we have something called like, instead of non-determinism, why don't we have like, non-determinism is like ORs. Why don't we have an AND non-determinism machine? Like we have a finite state machine that has two zeros coming out of a state, and instead of saying, I accept if there's a way to get from this to a final state, or there's a way to get from this to a final state, why don't I just make up a finite state machine, and the definition of whether I accept a string or not is if both these paths lead to a final state. This and this. I could make machines like that. Maybe they wouldn't be so natural, but if I had given you lots of assignments on it in the first week, you know, make a AND non-deterministic machine to accept this, you might have been able to think about it. Most of the examples I gave you worked for ORs, so it was easy to do it. But I could have given you examples that work for ANDs, and you would do that. Intersection's really easy if you have ANDs, right? So you could have done lots of intersection problems this way. In some sense, it's an accident that this was never defined, because 15 years after non-determinism was defined, this was defined. And it was defined in more generality. Here's how it was defined. It says you make a finite state machine, and every state you have to tell me whether it's an OR state or an AND state. If it's an OR state, it's like regular non-determinism. But if it's an AND state, that means both these have to find accepting configurations. And a string is accepted by this machine only if there's at least one path out of every OR, and all the paths out of every AND end up in an accepting spot. That's called an alternating finite state machine. As you might guess, every alternating finite state machine can be converted to a deterministic finite state machine. And it's this big conjunctive normal form connections of ANDs and ORs that you hold in the states. Remember, we used to hold just the ORs in the states, this or this or this or this. So now if you do that construction, you get this and this and this, or this and this and this, or this and this and this, just like conjunctive normal form. And it works the same way, and there's only a finite number, and you solve the same. Alternating finite state machines the same as regular finite state machines. But you know what happens when you take an alternating finite state machine that has n states and you convert it to a deterministic finite state machine? What happened when we took a non-deterministic machine and we converted it? What happened to the states? Potentially they exploded to 2 to the n. So you know what happens here? It explodes even a little bit worse. So people then, 15 years after non-determinism, figured, well, let's make an alternating Turing machine. What the hey? And actually, alternating algorithms are very useful, because sometimes you can think about how to do an alternating algorithm abstractly, and if you know how to convert it to something real, you can take an idea that you never would have solved normally, and you could solve it by solving it in the alternating land and then converting it to something in polynomial time. So it's not just whiz out, abstraction. It actually is really helpful to solve real problems. But in any case, I don't think when it was invented to solve real problems. It was invented because it seemed cool. And let's see what happens if you make an alternating Turing machine. So just to give you a sense of how nice this diagram is and what people like, it turns out that if you make an alternating Turing machine and you give it log space, log n space to an alternating Turing machine, this is the exact same thing as polynomial time. So that's like a beautiful result. Like out of nowhere, you make up this weird extra AND thing for a Turing machine. You give every state an AND or an OR. You give it log n space. And it turns out not to be a funny looking shape that overlaps all these things in a twisted way, but coincides directly with what we have as the most intuitive class in the whole list. Yeah?
Does that mean that any Turing machine we can build that solves a polynomial problem can be built with an alternating one?
In log n space. That's exactly what it means. And vice versa. You make a Turing machine that takes log n space and it equals p. And like I told you before, there are definitely, even in my relatively modest research career, I've come up with problems that I could immediately see how to solve those problems with an alternating idea using log space, and I didn't see the polynomial time algorithm to begin with at all. It really was obscure. And the way I found the polynomial time algorithm was I wrote this down, and then I went through the construction that I know because I understand why these two are the same, and then I actually wrote the code. So it really is practical, and it really does help. But it's even better than this. It's like, all right. There's another one just like this, but I'll talk about it when I talk about alternation, because I'll talk about this another time. I just wanted to give you a little sense that where things fit in this picture and what people like about this picture. And we'll refine it and talk about it a little more. What I want to do now is, I got two things. I want to do Savage's theorem and a reduction. And I like these both, so let me do the reduction first. All right, you've seen a lot of NP-complete reductions, but nobody here, as far as I know, has ever seen a p-space complete reduction. And if you remember how reductions work, you take every single thing in p-space and you reduce it to the problem you want. And that first reduction is a real bitch. That's the one that takes an arbitrary Turing machine and takes its transitions and converts it somehow to your problem. We never did that for satisfiability. I just told you it's in the book, and I said you can take any non-deterministic Turing machine, polynomial time, and convert it to a satisfiability problem. I said, take my word for that. It's too tedious to do. And then we went ahead and did reductions from satisfiability to, I don't know, to vertex cover, to Hamiltonian circuit, to other problems. And we showed that they were hard too. So today, I'm going to tell you the equivalent of 3 satisfiability for p-space. It's over here. It's called QBF, Quantified Boolean Formula. I'm not going to go through this reduction the same way I didn't go through the one for 3-sat, but I am going to show you a reduction from this problem to another problem, one that we mentioned the other day. And this reduction is in your book, so actually you don't have to take notes on it if you don't want to. Just sit and listen and think. All right, so first I need to tell you what quantified Boolean formula is. I mentioned it yesterday, but I'll mention it again now. It's very much like satisfiability, except this time, instead of just trying to come up with trues and falses that make the formula work, it's a game that you play with an opponent with alternating quantifiers. The best way is for me to show you an example. There exists an x1 for all x2. There exists an x3 such that all this should be true. x1, x2, x3 bar. This is just an example. x1 bar, x2 bar, x2 bar. You could have duplicates. x2 bar, x3, x3. So it's the same kind of thing where you have 3 variables per clause. You can have as many clauses as you want. This is sometimes called 3 QBF. But instead of just trying to find out whether this is true, it's got to be true according to these quantifiers. That means there's some x1 such that for every x2, there is some x3 that makes this true. So let's try to solve this together. And I want you to get the game sense of this as we try to do it together. I will pick the x1. I'm making x1 true. We're trying to find out, we're trying to discover the truth as a class. Can this formula be made true or not? The way to discover the truth is I try to make it true, and you try to make it false. Because there exists has to make this thing true, and then for everything, whatever you try, you got to keep trying to make it true. So you try to be my adversary. You try to make it hard for me. There exists, I have a choice. Here I don't have a choice. When I don't have a choice, you need to make it as hard as possible. When I do have a choice, I need to make it as easy as possible. Together we'll find the truth whether this is really true or not. So let's say I pick x1 true. So I got this guy true.
Pick x2 true or something.
No, so you can pick x3 true, and then
It doesn't matter.
If you pick x2 true,
Yeah, then that the middle.
if I pick x1 true, now I have to be able to continue for any value of x2 and find an x3 that makes this formula true. But if you pick x2 equals true, that means x2 bar is false. That means this clause is false. Since I picked x1 true, this is false also, right? False, false, false. And I can't win. I can pick x3 to be anything, but this clause ends up being false. So I'm going to go back. So I didn't succeed making this formula true. I'm going to go back and I'm going to pick x1 false this time. So now I took care of this one. And now it's your turn. You've got to try both values for x2. Well, false. If you pick x2 false, I'm OK, right? No?
Well, you can't pick x3.
Let's see. I pick x1 false. And you guys want to pick x2 false. So if x1 is false, x2 is false. That means I'm going to have to pick x3 equal to false. That's my only choice to get this one to work. But if that's true, then I can't do the last one. So what's the answer to this question? Is there a satisfiable formula according to these rules? The answer is no. All right? Because whatever I tried here, there was some way for you to mess me up such that whatever I tried here, I couldn't fix it. Now these quantifier alternations can go forever. They go as long as there are variables. So if there's 30 variables, you have these quantifiers alternate 30 times. You can see that this is a harder problem than the other problem. The other problem, you just have to come up with some way to do it. Here, every time I try to do it, you guys are getting in my way. And that's what it is. It's a back and forth fight to try to make this true, and you guys try to make it false. And together we discover the truth. Just like if we play chess for 2 to the 30th centuries, we will sooner or later discover the truth of who wins when they move first. Right? If we sooner or later play all the games, we'll know how to play perfectly. That's what we're doing here, but we're actually playing all the games, and we see who wins. And this time you won. The universals win, and when the universals win, that means the formula cannot be satisfied. When the existentials win, that means the formula can be satisfied. Everybody get a sense of this? Okay. Right, you know what? I'm definitely going to finish this today, but I'm not going to do Savage's theorem today. I'm going to do this a different day when you're clean and clear, and I don't have to keep you late. So let's finish this one idea today, because this is going to be nice, and I'll leave Savage's for a different day. Tomorrow, maybe.
Are you going to do the recursion theorem?
I wasn't going to, but I will if you want.
That's so cool.
Neil wants me to do the recursion theorem. That's a theorem that says that a machine can basically look at itself and spit its own description out on its tape. This is like a fun puzzle you give to beginning students anytime they learn a programming language. You say, write me a program that actually prints itself out. So here, print. Does that work? Almost. This program, when you run it, just does this. And I want it to do print. So at first you think about it for a while and you go, there's no way to do it. But you need just a little bit of a breakthrough, and you figure out a way to write a program that can print itself out. And that's exactly the trick in the recursion theorem. It's the same trick. If you can figure out how to do this for a programming language, you can figure out why the recursion theorem works. But I'm completely off on a side thing, and I'm not going to do this right now. You know what, maybe I'll do it as a recitation, or I'll do it as an optional thing. Just as a side point, I'm trying to finish this class on Friday, and I definitely will get to and beyond what I think is a reasonable amount for one semester. Nevertheless, as you probably can guess, there's 100 other things you can do in this class. You can go on for another course, and then a graduate course, and a few more. So if there's people who are interested in things like this or other things, I'll be happy to run like little small recitations next week when we're doing that Unix workshop week, you know, just as you know, interesting things. Because there's a few things that we definitely won't have time to do that are still fun, and I'll do that stuff. But now we're getting back to this. Yeah, it is really cool. You're right, Neil. It is really cool.
Didn't he interrupt?
That's all right. I like getting interrupted because I get to talk more. All right. Where were we? Quantified Boolean formula. Let's try to decide how we'd solve this. You're going to write a program to do this. How would you do it? How do you write a program to solve this? I want to get a sense of where this sits. I mean, I told you it's out here in polynomial space, but how do you know that? How come it's not polynomial time? How come it's not non-deterministic polynomial time? After we figure out where this is, we're going to convert this into a completely different form to show that a very different problem is p-space complete. But before we do that reduction, let's just analyze this problem and see how long it takes to solve it. How would you solve this problem? What is there to do?
Is this satisfiable? And then at the next level up, you would do a satisfiable Boolean problem. Is this unsatisfiable?
Yeah, what you're saying is right, but I wouldn't call it min-max. I'd call it and/or. We're going to actually write it out. We have two choices for x1, true or false. If either one of them work, then I win. And once I choose one of them, I have two choices for you. They both have to work for me to win. Then I'm back to the or level. I get to choose. If one of the two works, I win. Now I'm at the bottom of my tree. What do these represent? They represent actual formulas that I can plug values in. This is a choice of true, false, true, false, true, false. This is x1, this is x2, this is x3. Right? So when I get down to the bottom here, say to this one, this represents x1 is false, x2 is false, and x3 is true. and we check it. We check that formula. We check this formula. If these are both one or the other, if one or the other of these is true, then I mark this as true. I work my way back up this tree. An OR gets marked true if one or more of its children is true. An AND gets marked true only if both of its children are true. And if this reminds you of alternation a little bit, it should. That's why I mentioned it. And when you get to here, if this or this ends up being true, then you mark this true. If the thing up here gets marked true, you answer yes, there's an assignment. And if the thing up here gets marked false, you answer no, there's no assignment. Now, how long does it take to do this? How big is this tree? There's only 3 variables here, and we generated a tree with 8 leaves. If there were n variables, we would have generated a tree with 2 to the n leaves. We do an assignment calculation on each one of these. So that takes, 3 steps for each one to calculate a true or false. And then we got to take it and run it back through, doing ORs at each node or ANDs at each node. So that's going to do a number of steps equal to all the internal nodes. That's going to double this. There's as many nodes here as there are nodes here. So 2 to the n plus 1 time to go ahead to do this. Exponential time to solve this problem. Way out here. Can we do it in p-space? Could we do it in non-deterministic polynomial time? We could do regular 3-sat in exponential time, but when we try with non-determinism, we get it to polynomial time. How do we do that? We just guess true and false values. We do that in 3 steps, and then we check it in linear time. How come I can't do that now? 3 satisfiability gives me the same tree, the same exact tree. True or false for x1, true or false for x2, true or false for x3. The same computations at the bottom. If this was regular satisfiability, everything's exactly the same except for one thing. What's different about QBF compared to regular satisfiability?
It's not enough information just to have one guess.
Right, but you're right. But more specifically and more obviously at the top level. If I do this for 3-sat, I got the same tree, the same exact thing, 8 things in the bottom. And if one of these turns out to be true, then I say true. What's that mean? That means each of these nodes on the top are what kind of nodes? They're OR nodes. And if they're OR nodes, I just have to guess a sequence through, and I get it for free with non-determinism. The problem here is that I got these AND nodes at different levels. So here's what an accepting computation looks like. It's not a line anymore. It ends up being this kind of a subtree. And I don't get this for free in parallel. I don't get ANDs for free in parallel in non-determinism. I actually have to go down both and check it. So because of that, maybe I cut it down halfway, because half the different nodes I can take advantage of them, but the other half I can't. So maybe I get 2 to the n divided by 2. But it's still exponential. So I can't do this in non-deterministic polynomial time. I can't do it in non-deterministic polynomial time, or at least I don't see any way to do it, because the ANDs have to be traversed themselves. You don't get those in parallel. If it was an alternating machine, you could do it. But you don't have an alternating machine. But how do you do it in polynomial space? Same trick as we did before. Don't go ahead and store the whole tree, which gives you this exponential stuff. Just go down a single path and work your way back up, remembering that this is an OR node, just like you did with a depth first search if you did the Go problem in algorithms. When you come back to a spot, you got to determine if you're going to take those pieces off. So remember whether all the other paths out of there were surrounded. You remember that this is an OR node and that this is an AND node. And you just go ahead, depth first search, and you back up, and you go ahead and see if one or more of the things that are coming back ended up being true, and here, if all of them coming back end up being true. You can traverse through this tree space-wise, keeping only one thread through the whole tree. Right? If you get that, fine, and if you don't, we'll go back on it again, because understanding why things are in p-space takes some practice. But that is supposed to convince you that QBF is in p-space, that we can go through this tree by keeping only one thread through the tree at any time, backing our way up and down recursively. All right, I don't want to spend too much more time on it because the reduction itself is more interesting and easier to understand. So that convinces us that this problem is in p-space. Now I'm going to show you that there's another problem that is p-space complete because this problem reduces to it. And I'm going to do a reduction example directly from this example. All right, so here's the problem we're going to do. We're going to do the geography game that I told you about yesterday. QBF reduces to geography. Geography is that game where everybody gets a book. And this is regular geography, not my weird version where people play by themselves, but the version where people play against each other. You pick a move, a country in the universe. The person continues with their move, starting with a letter that your country ended with. The way you think of it in mathematical terms or computer science problem-oriented terms is somebody gives you a graph, something like this. Say I start here, and these arrows represent that the last letter of this country is the first letter of this country. So I make dots for every country or geographical location, and I connect arrows according to the last letters and first letters. And then we play the game on this graph. I start here, and I move here, let's say. So now that's taken. Now it's your move. You only have one choice. There's only one country left. You go here. Now it's my turn, and I got no moves, and I lose. That's geography. You're given a directed graph. Somebody's got a starting place to move from. And the question is that first person going to win, or is that first person going to lose? I'm going to convince you that in geography, if you can figure out whether the first person wins or loses, then you can solve this problem. I'm going to convert any one of these problems into a graph. And if you give it to somebody who knows how to solve that game, and they tell me whether the first person or the second person wins, if the first person wins, there's going to be a satisfiable assignment here. And if the second person wins, there won't be a satisfiable assignment. Everybody with me on the plan? Yeah, Teresa?
Tell me where the universal is in the game over there.
Yeah, person number 1 is existential, person number 2 is universal. You're going to see it in a second. I'm going to go make the diagram. I don't know. I lost it, but I know how to do it by heart, so it doesn't matter. Here's the picture we're going to make. Here's the starting point. This is where I start. We're going to have a little diamond like this for every one of the variables. Remember how we tried to decide the truth or falseness of this before? I'm going to mimic exactly what we did before, but turn it into the context of a game. That's why we did that before. So this would make more sense. So here's what we're doing in this game. I start here, and if I go here, this represents x1 being true, and this represents x1 being false. So I move to the side that I think is true. Either x1 is true or x1 bar is true. Right? And now it's your turn. Where do you go? You go here. I'm just pushing you along in my game. And then I go here. And now it's your turn. Now you're going to choose for x2 whether x2 is true or x2 bar is true. This is kind of the setup. We're marching through this game. There's not too many choices. All my choices have to do with whether x1 gets used or x1 bar gets used. A true variable is one that's going to be used. And then you get to pick whether x2 gets used or x2 bar gets used. And we're going to do this one more time for x3. I have these little edges just to take up the space for the other person's move, to make sure that we alternate. So here's x3, x3 bar, back together. OK. So I might pick true. You go here. I go here. You might pick false. I go here. You go here. I might pick true. You go here. And now it's my turn. Is it my turn? I went here. You went here. It's the first person's turn. I want to convince you now, after we've chosen these true and false variables, that this whole formula is true. You want to convince me that one of these is not going to have a true variable in it, right? That one of these clauses is all false. So it's my turn here. I just go down. And now here it's your turn. You're going to pick the one that you think is false. You get 3 choices. Normally there would be arrows here for as many clauses as there are. Okay? Here's clause number 1, here's clause number 2, here's clause number 3. I'll call them C1, C2, C3. C1, C2, C3. If there were more, there'd be more. You choose one of these, the one that you think is false. And now everything's going to close up and you'll see how it works. I have to convince you, since you picked the clause, that that clause is really true. How do I do that? I have to pick a variable in there that's marked true. So here's what I'm going to do. C1, let's actually play this game. It'll make it more clear what to do. You guys win the game, right? Whatever I do, so it doesn't matter. Let's say I'm going to go here. I'm going to pick this side. You go here. I go here. Which side do you pick if I pick x1 true? Do you remember? x2 is also true. So you go this way. Then I go here. You go here. I can pick anything I want. I don't think anything works. Say I'll go here. You go here. I go here. Which clause now do you know has all the falses in it? That's where you want to go. Which one? The second one, right? All right, now what messes me up? What messes me up here is if the only way out of this spot is all falses, then I lose the game. But if there's a true out of this spot, then I win the game. But we marked all the true and falses really carefully, right? We put X's on all the true ones and open on all the false ones. So what edges should I connect here to make sure that the game finishes up right? If x1, x2, x3 is in a clause, then I should allow this one to exit on all the opposite values. Same thing here. Let's look at C2 in particular. Let's going to connect it to x1. Sorry, x1, not x1 bar. Connect it to x1 and to x2. When you picked this spot, you killed me. The only way for me to go out is to go to the two things that are marked false. To go to the opposite of the ones that were in there. So I lose the game. If you had picked this other clause, I would have had a way out. So where does this other clause go? C3 goes to x2 bar and x3 bar. And C1 goes to x1 bar and x2 bar and x3. The opposite of whatever these are. What's that? Oh, C1, not C2. Thank you. I'm going to erase these x's. We're going to play the game again. I didn't mean to imply that we create the reduction after we play the game. We don't. The reduction is set up like this. This is the graph. I want to know who wins the game on this graph when I start from here. Who wins this game? If you guys win the game, then there's not going to be any formula here. If I win the game, then there's going to be a formula here. So you know what? Can I change this formula a little so that I can win the game? Is there an easy way to do that? Then we'll play a game where I can win. Let's play this game again and see if you guys can win. I'll go this way this time. You have to go here. I have to go here. Which way do you want to go now? You guys go here. This corresponds to me picking this one true, corresponds to you picking this true. I go here, you go here. Now I go, say, this way. You go this way, I go here. Which clause do you want to pick now? If you send me back to C2 now, I'm going to win the game. I'm going to go out and go here, and then you lose. Because that's a bad choice for you guys. right? C2's got a true one open. But if you send me over to C1, if you go here, I'm blocked off here, and I'm blocked off here. If you can always send me to a clause that every single way out is blocked off, that means you sent me to a clause with all false variables in it. But if I can always find a way out, no matter which clause you send me, to a variable that's true, then I win the game. I've turned this problem of deciding the truth or falseness of this formula into a problem about a game, a kid's game. And if you can answer who wins on this kid's game, you can answer the question of this formula. So in this game, if we both play as good as possible, you guys will always win. The same way we can't get a satisfiable formula here. But if I change this formula around so that there was a way for me to win, you guys wouldn't stand a chance. I'd pick the right choice here. Whatever choice you pick, I'd pick the right choice there. Whatever clause you threw me in, there would be a way out because I would go to a true variable that's opened up here. All right, so let me stop for a second. Again, here's the reduction. 3 diamonds, 1 for each variable. 3 circles, 1 for each clause. Connect the circles to the opposite of what they were there, so that you connect them essentially to what are false values, to what are closed up. You leave the true values open. And then you play the game, picking variables. The adversary picks the clause. I pick the variable at the very end. All right, let me stop for a second. Questions about this?
For an even number of variables, you'd want to hook them up in the opposite direction, right? Because then it would be your turn to pick the clause.
You mean if it ended with a for all?
Yeah.
Yeah. Actually, I think you can assume that this game always starts with a there exists and ends with a there exists. QBF starts with a there exists and ends with a there exists. I don't think it ever ends in for all. But you could certainly do just what you said. If it did end in for all, you could just alternate the moves at the end with an extra edge to make sure that it gets alternated the other way, to make sure that the other person chooses the clause and that you choose the variable at the end. Sure, you can do that. Other questions?
I just don't get the last step. I choose C1, and what are your choices, and what is the ramifications of your choices? If I choose C1, and then you're saying you have a path to X1 not.
Yeah, let's.
You win or you don't win? I guess I don't.
It doesn't mean he doesn't have a valid move because you can't go to a place you've already been.
Oh, is that what the logic is? You can't go to a place you've already been?
Yeah, in this game, you can't use the same country that's been used before. So if something's been X'd out, then you lose the game. Yeah, that's very important, right? Without that, you can't see who wins or loses.
Okay.
Right. If the thing is blocked, you're stuck. So the only way you're open here is if you go to places which were not chosen before. That's why we put in the opposites here, because we choose the ones that are true, and then we leave open the ones that are the opposites of those. Does that make sense? Kind of.
Play the game again, though. I guess.
You want to? Let me just do one more thing, and then we'll quit. Let me make up a different formula, write out the game, and then we'll play the game and see if by playing the game we can figure out whether the formula is satisfiable or not. Don't look at the formula, just look at the game, and we'll try to do that. So I'm just going to make something up. There exists an x for all, I don't like x1, x2, x3. I'll just use y's and z's. And I'll just make this up. I have no idea if it works or not.
You're using X, Y, and Z.
You gotta wonder.
We do.
Oh, man. Oh, scare myself. I'm going to make 4 clauses this time, just for... Okay, I'm only using 3 variables again because the variables take up room, but the clauses don't take so much room, so I'm going to put 4 of those in. So don't think about this problem. Don't think about whether it's satisfiable or not. Let's just make the reduction to show that this reduction really works. Let's try to show that solving the game is going to help us solve this problem, and vice versa. So here's what the reduction looks like. Make sure you can do it. It's mechanical. It's very fast. We have a diamond. I won't put the arrows in. Everybody knows it kind of goes down. Okay? I got a diamond for every variable. So I got x, y, z. I connect them this way, right? I got another edge here. Then I go to the 4 clauses, 1, 2, I'll put 2 on this side, 3, 4. Now it's looking pretty. All right, let's do the opposites here. I'll just mark this x, x bar, y bar, so we remember what we're doing, z bar. This is going to be C1, C2, C3, C4. Okay, so C1, this is going to be x bar, y, z bar. So we do it to the opposites. This goes to x, help me, y bar, and z. Okay? The next one goes to x bar, y bar, and z. And now let's do this guy. X. Oh, color chalk. Very good idea. Color chalk, color chalk. Absolutely. That's the pink one.
Maybe it's used different colors.
I know, I know. I got another color. All right, all right. All right, so we got pink, blue, purple, and orange.
You're missing
What did I miss?
You're missing an arrow on each of those nodes.
From the bottom.
Oh,
That's from the bottom.
oh right, yeah, sorry.
Am I or am I not?
You're not.
Contradicting the fact that you're always right? It's my lucky day. All right.
Nothing to live up to.
That's right.
You're not
All right.
missing it yet, but soon you will.
All right, here we go. This one goes to X. Help me, Erica. Y. All right, and then the last one is orange, and it's going to go to X,
Not Y.
not Y, and Z. All right, fine.
Now let's play.
Doesn't that color help?
It's Picasso.
It's pretty. I kind of like it. Let's play this game. I'm not going to mark it up. We'll just play it, and well, I guess I'll have to mark it up. So I'll just fill in the circles as we go. All right, you guys want to go first or second?
First.
All right, first it is. You already checked. All right, which way do you want to go, Michael?
Let's go not X.
Go this way. Right. I go here. You go here. I'm going to go here. You go here. I go here. Your turn.
Not Z.
You go here. I go here. You go here. Now it's my turn. All right, so now I'm going to look for a good one. If I go here, you're going to be able to win by going this way or that way. If I go here, you're going to be able to win. If I go here, you're going to be able to win. You can win all everywhere. All right, so I don't like my choice here. I'm changing it. I'm going to go this way instead. Doesn't do a damn thing, right?
Nope.
Didn't fill in anything. All right, so you guys can win, but let's figure out the assignment that applies to that. You chose X being false. I chose anything, any Y, and you chose Z being true. Oh, false, good. So presumably, according to this set of choices, X false and Z false, this formula is going to end up being true. And I think we should be able to check that, right? X false, Z false makes this true, no matter what Y is. X false, Z false makes this true, no matter what Y is. X false, Z false makes this true, no matter what Y is. Same here. So you guys win. Now, I want to convince you that this is not an accident. This game is exactly what's going on here. This will have a solution exactly when you win. This will not have a solution exactly when you lose. If there was a way for me to pick well, so that whatever you picked here, I could pick a clause that was connected to all the things that were false, then all those things would have these white boxes on them. And that would correspond specifically to me being able to choose the middle variable so that when we were all done, no matter what you chose for X and Z, I found a clause in this collection of 4, all of whom were false. all of whom were pointing to things that you filled in there. You get it? Just to give you a sense. When I first thought of this alternate to this problem, you know, where you play on your own, so I had no idea because I had never seen this paper. But this guy that I was working with it on, my co-author, he's a big shot in this field, and he had seen this paper and many other papers like it, and he quickly sketches out this idea for a reduction, which to me just seemed like, you know, manna from heaven. Like, whoa, how'd you think of that? And then I found this paper later, and I figured out how he thought of that. But our things, you know, have two separate stuff going on, because people don't alternate from the same spot. You have to alternate from your own spot. But it's more or less the same idea. But just to give my co-author a lot of credit, because he was a very, very clever man, and he still is, notice something really special about this graph. Are there cycles in this graph or not? Definitely cycles, right? You start here, you go back. In fact, it's a fundamental feature of this reduction to have cycles. Everyone agree? If you try to do this reduction without cycles, you get no place. The whole idea is that you block things off on the way down, and when you try to come back, you get stuck. But it would be really interesting to know whether this problem, maybe it's easy if there are no cycles. Maybe it's only p-space complete when there's cycles. Is there a way to do this reduction without the cycles? So we thought about this, and it turns out that at least, not in this problem, I don't think, but in our problem and the other problem, our problem is actually a little harder. You can take an NP-complete problem and reduce it to this problem and get a graph that's just like this, but it's got no cycles in it. And the game is a win for player 1 if there's a vertex cover for the graph, and the game is a win for player 2 if there's no vertex cover for the graph we started with. So we made a reduction from vertex cover to this problem, and that reduction has no cycles in it. So that's a really cool result. In other words, this game is hard even without cycles, or the variation that I thought of when you have two people playing on their own. That game is hard even with no cycles in the graph. The only thing that makes the game easy is when it's a tree, when there's not even an underlying cycle. But if there's cycles in the graph, that's not the hard part. It's hard even when there's no cycles. The thing was, we couldn't show it was p-space complete. We didn't make that reduction from QBF. We made that reduction from vertex cover. We made that reduction from something that was sitting in NP. And this problem is probably way out here. So it's not as good and not perfect, but we showed that the problem when you have no cycles is NP hard. Everything in NP reduces to it, but we don't know that it happens to be an NP. That's unknown. All right, so there's an example of an NP hard reduction that's not as good as a p-space complete reduction, but still good because the p-space complete reductions have these more general graphs, and at least the NP hard reduction had a more specific constrained graph. So it's still an interesting idea. And that reduction is hard to understand. That's not as easy as this. And if you look at this paper that I have, you know, there, and you take a glance at it, there's this funny picture. It looks like a cigar with all sorts of. It explains it, but it's a little tricky. All right, so I want you to see this reduction and get a good understanding of it. This is very typical of the reductions that come p-space complete. We're not going to do too many more of these, but we are going to do some. In homework, I'm going to ask you to do one NP complete reduction and one p-space complete reduction.